All right, so let's start the second part of chapter 4 lecture. So to start for today's, before I start today's lecture, let me briefly review what you already learned in last lecture. Okay, so in last lecture, you learn about force, and then you learn about Newton's laws of motion. Okay, so you learn about three laws. Okay, first law, second law, and third law. And these three law basically um, tell you about the relation between force and motion, object's motion. Okay, the first law was when net force is equal to 0. Okay, when net force is equal to 0, then we see that an object is if an object is at rest, it stays at rest. If the object is in motion at a constant speed in a straight line, it is in a straight line at a constant speed. Okay, so that is the first law. The second law is if net force is not equal to 0, then this net force is equal to ma. Okay, force equal to mass times acceleration. And actually, to solve problem, we need to break this into its component, and the x component equation is this one. Okay, and y component equation is this one. Okay, so this is the Newton's second law. And third law tells us that every action has its equal and opposite reaction. Okay, so these are the three laws. And then we learn about the normal force. For the normal force, we use this symbol or this symbol. Okay, and normal force is always perpendicular to the surface. Okay, so this is 90 degree. So if we have a plane surface, the normal force is this one. If you have inclined plane, something like this, okay, when the object is somewhere here, the normal force will be in this direction, so that this angle is 90 degree. Okay, so normal force, in many problem you will see that the normal force balances the gravitational force. So if the normal force balances the gravitational force, then normal force is equal to the gravitational force. Oh, okay, so gravitational force we also learn, and you see that the gravitational force is equal to mg, or W equal to mg. Okay, so in many problems you will see that the normal force and the gravitational force are equal and opposite. So for example, if we have an object somewhere here, and if there is no other force acting on the object except the gravitational force and normal force, okay, then the normal force is equal to the gravitational force. Okay, but it is not always the case. All right, and then you learn about you learn about the free body diagram. Okay, so let me briefly review free body diagram and then move to two new forces you are going to learn in this lecture. The first one is the tension, and then another one is the friction force. Okay, all right, so let me briefly review the free body diagram. So free body diagram is important to solve a problem, force related problem. So when you have a problem, okay, in this chapter, the first thing we should do, we should draw a free body diagram. That will be easier to solve a problem. Okay, it doesn't mean that without drawing the free body diagram you cannot solve a problem, but free body diagram helps you to graphically understand the problem. Okay, so what is the free body diagram? Free body diagram is a diagram graphic to show all the forces and the direction of the acceleration of the problem. Okay, so the first thing, when you draw a free body diagram, you have to identify all the forces that acts on an object. Okay, so in the last class, we see that we have a box on a surface and someone is pulling this with a force Fp. Okay, that makes an angle 30 degree with this horizontal line or a line parallel to the ground. Okay, so when we have a problem something like this, first thing is we have to choose a coordinate system. So normally we choose this coordinate system. This is our usual coordinate system, but sometimes the coordinate system may be a little bit different. So we'll be discussing this today, at least for an inclined plane problem. Okay, so when we have decided our coordinate system, okay, then we should put the box or the object at the center of the coordinate system. Okay, so sometime in many problems you will see that more than one objects are there. So if we have more than one object, then we have to draw individual free body diagram for each object. Okay, all right, so in this problem we have the object, the box, and then we should have this one, right? The gravity mg. We have normal force n, and then this one is Fp, right? Now, because Fp is neither along the x or y axis, so we have to break it into its component. Okay, so how to break it? We already know how to break it. So we have to draw a perpendicular line from the tip of the vector to the horizontal axis, and then another one that connects this perpendicular line. So the line that is parallel to the y-axis, we call it y component, and the one which is along the x-axis or parallel to the x-axis, we call it x component. And because this is opposite of the angle, opposite is related to sine theta. Okay, so it will be sine theta, and it will be cosine theta. Adjacent is cosine theta. Okay, so if this is theta, then these are the fpx and fpy. Okay, and then when you pull this object in this direction, the acceleration will be only in this direction. Okay, so we should also draw a vector for the acceleration, and that means we have only acceleration along the x-axis. There will be no acceleration along the y-axis for this problem. Okay, so once we have all this information in the diagram, then we have to write two equations. Okay, fx equal to max and fy equal to may. Okay, and then solve the problem. All right, so we will see that we will see this when we solve some problems. Okay, all right, so now let's go to the slide. Okay, so today the first force we are going to discuss, we are going to learn, is the tension force. So to represent the tension force, we use these two symbols. Okay, either ft, f subscript t, or just t. Okay, so both are the same thing. Okay, sometime in some problem you probably see that I use t or f subscript t. Okay, both are tension force. So tension force, what is tension force? Okay, so tension force is involved when objects are connected by string, rope, or wire. Okay, so you probably see this kind of thing in some problem. Okay, so let me show first and then discuss. So you probably see something like this. Okay, so these are some example you will see, And if we have some example, something like this, tension is involved. So here you see this object is connected by this rope, okay, or a string. So that means we should have tension here. So here we have these two objects connected by this rope. So if we have some situation, something like this, then we have tension force. The same thing here. The same thing here. Okay. So these are some typical example you see. So when, I mean, the bottom line here is when objects are connected by some string or rope or wire, we should have tension force. Okay. Now, I mean, how to draw the tension force. Okay. So we have to remember, when we draw the tension force in a free body diagram, or when we solve a problem where we have tension force, we have to remember few things. Okay. The first thing is tension force is always parallel to the string. So if you look at all these examples, here you see that it is along the, so here you see that it is parallel to the string. Here it is parallel to the string, 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 parallel to the string. So the tension force is always parallel to the string. So the first thing. Okay. The second thing is it is always opposite to the it is always opposite to the applied force. Okay. What I mean by this is this. So let me go back to the picture. So here you see this is the applied force. Okay, so in this object, this is the applied force, right? So the tension force is opposite to this applied force. So in this object, the tension force will be this one. Okay. So this is the applied force. The tension force is this one. Okay. Now, how about this one? So how about the other problem? Okay. So here, so for example, this one, I don't have the applied force. Okay. So because there is no applied force, but this is applied, I mean, the way the gravitational force is applied to this string, right? So here we can think that this is the applied force in this string. Okay. So because the gravitational force is in this direction, the tension will be opposite to this gravitational force. Okay. So that's why I say that tension force is always opposite to the applied force. Okay. So the same thing here. So here you can see that this is the gravitational force. This is gravitational force. You can treat this as an applied force, and then this is the tension force. The same thing here. Okay, the same thing here. So the gravitational force, and this is the applied force on this object. Okay, so tension force is parallel to the string, and it is always opposite to the tension, opposite to the applied force. Okay, so applied force could be the explicit applied force, or it could be the gravitational force. Okay, so that this is the second rule. The third rule tells us that, let me read this and then explain it. Okay, if the mass of the rope is negligible, okay, and if the pulley is massless and frictionless, normally in this chapter, I mean, the pulley and the rope are assumed to have negligible mass, and the pulley is assumed to be frictionless. Okay. So if the rope is negligible, a rope has negligible mass, and the pulley is massless and frictionless, then the magnitude of the tension force, so let me read it. The magnitude of the tension force is the same at the two ends of the rope. Okay. However, the direction are opposite. So once you know the tension force at one end of the rope, okay, we can determine what happened to the other end of the rope. Okay, so let's go to the pictures and then discuss. Okay, so it says that the magnitude of the tension force is the same at the two ends of the rope, however the direction are opposite. Okay, so what it means is this. Okay, so first so here this is the object. Okay, so this is the object, this is the applied force, so the tension force will be this one. Okay, now that rule tells us that at the other end of the rope, so this is the rope, okay, the other end means this one, at the other end of the rope the tension force will have the equal magnitude if the mass of the rope is negligible. Okay, so if we assume that the mass of this rope is negligible, the tension, the magnitude is same, so if it is T, it will be the same T, but the direction will be opposite. So the direction was this one, so here it will be this one. Okay, so that is the third rule tells us. Okay, so remember this. Now how about the other here? So for example, we already see the tension will be here. Okay, for this one the tension will be this one, because this is opposite to the applied force here, the gravitational force. Okay, now if the pulley is frictionless and massless and the rope is massless, the other end of the rope is this one. So here we should have the tension force of equal magnitude. If it is T, it should be T, but you see the direction is this one. Okay, but direction should be opposite on the other end, so the direction should be this. Okay, the same thing here. So this is the tension force, the other end. Okay, the T is the same. Okay, the magnitude should be same, but the direction should be opposite. The same thing here, you see this is other end here. Okay, so the direction is this. So the rules are tension force are we have tension force when when the objects are connected by strings, wire or ropes. Tension force are always opposite to the applied force. Okay, if the ropes are massless and the pulleys are massless and frictionless, then at the other end of the rope, the tension force, the magnitude of the tension force will be the same, but should have opposite direction. Okay, now if the same rope accelerates, the same rope accelerate at the same rate if the rope does not stretch. When for example here, the last rule tells us that if the rope or the ropes does not stretch, do not stretch, okay, then the acceleration of all the object connected by the ropes should have the same acceleration. Okay, so for example here we have two objects connected by a rope, right? If we have something like this, the acceleration, the magnitude of the acceleration will be same for both objects. Okay, so here we have two objects, the acceleration for this one and this one will be the same. Okay, the same thing for this one. Okay, so we have two objects. Okay, we have two objects here. Okay, so for this one and this one will have the same acceleration. Okay, and the condition is when the rope does not stretch. Okay, so if the rope does not stretch, normally in this chapter we don't consider this to make the life simple. So for all problem in this chapter, okay, will have the same acceleration if the two or more objects are connected with ropes. Okay, so for example here we have two objects connected by one rope. Let's say we have three objects connected by two ropes. Okay, something like this. So this is applied force. We know that there will be tension here. Let me call it T1, and then at this point the tension will be again T1, but in the opposite direction. Okay, now this rope is different than this rope. So the magnitude will be different. So here we'll have T2, and then here we'll have T2. Okay, so even though if the ropes do not stretch, all the object will have same acceleration. Okay, so this is basically the assumption of this chapter. Okay, and later, I mean, we may, if we consider if the rope stretch, then the acceleration will be different and the problem will be more complicated. So we are normally don't, I mean, we are not going to solve a complicated problem here. All right, the last thing here we are going to learn is the friction. Okay, so far we basically neglect friction, but we cannot avoid friction. Okay, so we need to understand friction. Okay, so in this chapter some of the problem will be ideal, that means we neglect the friction, and then later we add friction, because this is some real life problem, right? Friction, without friction we cannot think many things. Okay, for example, if there are no frictions between the car tires and the ground, it will be very difficult to drive. Okay, now what is friction? Okay, and why we have friction? Okay, so we have friction between the two surfaces. For example, let's use this example. Okay, so between the table and the ground, okay, we have friction. Although it looks like the smooth surface, the bottom of the table and the floor looks like very smooth, but if you look microscopically, you will see that they are not that smooth. Okay, so you see that. Okay, they are not smooth. Okay, so because of this we have friction. Okay, now before I talk details of this friction, let me go to the simulation and show some simulation and then come back here. Okay, all right. So earlier we neglect friction. Okay, so now let's I mean discuss a real life problem where there is friction always. Okay, so if we have friction, okay, so what happened? So you see that earlier when there was no friction, you see that whenever we apply a small amount of force, it moves, right? It moves to the right. Okay, now let's see what happened. Let me apply 10 Newton. Okay, 9, 10. So you see that when I apply 10 Newton, nothing happened. It doesn't move. The speedometer shows the 0 meter per second, right? But last time you see that it was moving, right? The same box, same robot, but now we have friction. So because of the friction, it's not moving. Okay, so I mean, this robot applied some force, 10 Newton, but here now this time you see that this 10 Newton force is balanced by something. Okay, so here we call it friction force. Okay, so when we have a heavy box, okay, let's say we want to move a heavy box in our I mean from our living room from one side to another side. Now if we push gently, okay, you probably are not able to move that box. Okay, so what happened? You push means you apply some force. So if there is net force and if it is not equal to 0, it should move, right? If the object does not move, that means the net force is equal to 0. Okay, so how I mean how the other force come to place in the object? The answer is the friction force basically takes place here. Okay, so when you push an object, okay, if push a heavy object, if the if you are not able to move the object, that means friction takes place here. Okay, so here you see that this robot is applying 10 Newton force to the right. Okay, and because the object is not moving, that means this 10 Newton force is balanced by something else. Okay, and here the something else is the friction force. So friction force takes place here. Okay, so you see that 10 Newton is balanced by 10 Newton. Now let me increase it. Let me increase it to 20 Newton. So you see that again 20 Newton is balanced by 20 Newton. How about 70 Newton? Okay, so I now change it to 70 Newton. Still we can, you see that it is at rest. That means the 70 Newton applied force is balanced by friction force. Okay, so that means the force is not enough to move this box. Okay, now you know that if we keep adding more forces, okay, at some point we'll be able to move it. Okay, so that means the friction has some maximum limit. Okay, so let's see what is the maximum limit for this one. Okay, let me add 50 more Newton here. So 120 Newton. Still this 120 Newton is balanced by the friction force. Okay, so that means we didn't reach to the maximum limit. Okay, let me now add 1, 2, 3. Okay, so still it's not maximum limit. Okay, so you see that before we reach to the maximum limit, okay, the applied force is balanced by the friction force. Okay, okay, applied force is balanced by the friction force. That means the sum of the forces is equal to 0. Okay, applied force is 124 Newton, friction force is also 124 Newton. Okay, but as I told you that it has some maximum limit. Once we reach to the maximum limit, it will start moving. Okay, now let's see, how about 125? Still it is balanced by the friction force. Okay, how about 126? So so you see that here you see two things. Okay, the first thing is when we have 126 Newton, okay, it starts moving. Okay, that's the first thing. So that means 126 means we reach to the maximum limit. So we already overcome the friction force. And when we overcome the friction force reduced to 94 Newton. Okay, so sorry, yeah. No. Okay, so you see that, let me draw it again. So you see that, no. All right, so you see that when we have the applied force equal to 125 Newton, it's balanced by the friction force, there is no motion. Okay, when we have 126 Newton, so when we have 125 Newton, the sum of the force is equal to 0. Okay, so here you see the net force is equal to 0. So there is no motion, the speedometer is 0 meter per second. But whenever we have 126 Newton, okay, applied force, two things happens. Okay, okay, so here you see that when we have 126 Newton, it starts moving. You see that now the speedometer is not 0 meter per second, so that means it starts moving. Okay, I just pause it to talk about that, and then I will play it. Okay, and another thing is you see that the friction force drops to 94 Newton from 125 Newton. Okay, so two things happens when you overcome the maximum friction force. Okay, so one is it starts moving. When it starts moving, friction force reduced to some lower value. Okay, so this tells us two things. One thing is there are to move an heavy object, we have to overcome the maximum limit of the friction force. Okay, once the object starts moving, once we overcome that maximum limit, the object starts moving, and when it starts moving, the friction force reduced to some lower value. Okay, so it tells us that we have two types of friction. One is kinetic friction, another is static friction. Okay, so the static means when the object, static means object at rest. Okay, so static friction take place when the object is at rest. That means you are applying the force, but you cannot move the object. Okay, so if you are applying the force but you cannot move the object, then the friction we have between the object and the ground is the static friction. Okay, and when it starts moving, okay, the motion is related to the kinetic. So when it starts moving, the friction between the object and the ground is basically the kinetic friction. Okay, static means at rest, kinetic means in motion. Okay, so when the object starts moving, the friction between the object and the ground is the kinetic friction. When the object is at rest, the friction between the object and the ground is the static friction. Okay, all right, static and kinetic. Now the kinetic friction is low. Okay, so so the kinetic friction is low. That means when it starts moving, the kinetic friction, you see that it is 94 Newton. Okay, so yeah, so I again screwed up. So 125 is the maximum limit of the static friction. Okay, so once we overcome the maximum limit of the static friction, it becomes kinetic friction. So you see that kinetic friction is 94 Newton. Okay, so why we have this? Because it's difficult to start moving an object. Okay, so once it starts moving, it's easy to keep moving. Okay, so that's why the kinetic friction is lower than static friction. Okay, static friction means you are applying force but you cannot move it. Kinetic friction means it starts moving. Okay, so when an object is moving, the friction between the object and the ground is the kinetic friction. Okay, so the static friction, the kinetic friction is lower than the maximum static friction. Okay, remember that. Now let's go back to the slide, study guide slide, and see what is the mathematical details of static and kinetic friction. All right, so you see that try to understand this graph. Okay, so here you see that you are applying force. Okay, this is the applied force direction and this is the friction. Okay, the y-axis is the friction. So as you already see that at some limit, so this is the maximum. Okay, maximum limit. Okay, so before you reach the maximum limit, okay, the applied force is balanced by the friction force. What it means, if the applied force is 10, the friction force will also be 10. Okay, so you see that here. So if it is 10, if it is 10, it will be 10. If it is 20, it will be 20. If it is 30, it will be 30, and so on. Okay, So um, and then once we reach to the maximum friction, I mean maximum limit of the static friction, then you see that it drops, okay, and it stays constant. Okay, so here you see that we are increasing the applied force, but the friction stays the same. Okay, so that means before you reach the maximum limit of the static friction, the applied force is balanced by the friction force, so that the object is at rest. So once we overcome the maximum static friction, the object starts moving, and when the object starts moving, the kinetic friction takes place, and the kinetic friction is lower than the maximum limit of the static friction. Okay, so you see that this is 40 or close to 40, and this is 30, and the kinetic friction is a constant. Okay, so you see that you are applying force, but there is no change in the kinetic friction. Okay, so that's basically the things about friction. But what are the equation? Okay, equation for the frictions, kinetic and the static friction. Here we have these two equations. Okay. The static friction, the maximum, so we already know that if we are not at the maximum limit of the static friction, so the friction force is represented by this one. Okay, so if we don't reach to the maximum limit of the static friction is always equal to the applied force. Okay, so this is one of the equation. So once we reach to the maximum limit of the static friction, the definition of the maximum limit of the static friction is this one. So mu s times Fn. So if you remember, Fn is the normal force. Okay, so this is the normal force. Okay, so the maximum limit of the static friction is mu s. I'm going to talk a little bit about this. So this symbol is called mu. Okay, is a Greek symbol, and the subscript s to represent subscript s is to represent it, the static friction. Okay, so the mu s times the normal force. Okay, for many cases the normal force is equal to the gravitational force, but not always. Okay, remember that. So this mu s we call the coefficient of static friction. Okay, and the same thing for the kinetic friction. Kinetic friction is mu k. Mu k means that it is the coefficient of the kinetic friction times the normal force. Okay, so for static friction we have to use mu subscript s, and for kinetic friction we have to use mu subscript k. Mu k means the coefficient of kinetic friction, and mu s is the coefficient of static friction. Okay, and then as you already see from the simulation and the graph in the last slide, that the kinetic friction is lower than the maximum limit of the static friction. Okay, so because of this, the coefficient of static friction is always higher than coefficient of kinetic friction. So here in this table you can see that for most of the surfaces, this column is higher than this column. Okay, all right. So the last thing in this chapter, I mean in this lecture, I am going to teach is the inclined plane. Okay, so for inclined plane, all the things are very similar to the things you learned in this chapter. Only thing is different is the coordinate system. So normally we use this coordinate system. Okay, so normally the coordinate system is this. So if the object is on an inclined plane, something like this, okay, then the coordinate system needs to be modify something like this. Okay, so if you modify something like this, it will be easy to solve the problem. Okay, I mean, it doesn't mean that you cannot solve the problem with this coordinate system, but it will be easier to solve the problem um, if we modify the coordinate system. I mean, if we rotate the coordinate system something like this way. Okay, so when we have a inclined plane problem, normally these the perpendicular to the surface is used as the y-axis. Okay, and the parallel to the plane is used as a x-axis. Okay, something like this. Okay, sometimes we use this as our x-axis, sometimes we use the positive x-axis, and sometimes the other way, the positive x-axis. So we'll solve some problem, and hopefully that will clear this concept. Okay, all right, so now let's say we have an object on an inclined plane, something like this. Okay, so what forces act on this object? Okay, so if we have this, okay, this object here, we have these forces. So gravitational force is directly downward. So this is the gravitational force. The normal force is perpendicular to this surface. So this is the normal force. Okay, so here you see that this is the normal force, this is the gravitational force. And if we include the friction force, right, the friction force will be always opposite to the motion. So you already see that in the simulation, right? So friction force acts always opposite to the friction. Okay, so if the object moves in this direction, okay, if the object moves in this direction, the friction force will be in this direction. Okay, so the friction force will be in this direction. So this is the friction force, this is the normal force, and this is the gravitational force. Okay, so here in this picture you see that the normal force is this one, gravitational force is this one, and then this is the friction force. So you see the motion is in this direction. So if the motion is in this direction, the friction force will be opposite to the motion. I mean, the direction of the friction force will be opposite to the direction of motion. Okay, so now the only problem here is, so if you look at this one, so you see that this is our y-axis and this is our x-axis. So the problem is this is okay because Fn is to the y-axis and the friction force is along the x-axis or negative x-axis. The problem is this is neither along the x nor along the y-axis. The gravitational force is neither along the x nor along the y-axis. So if we have some problem, something like this, then what we have to do, you already know what we have to do, right? So because it is neither along the x-axis nor along the y-axis, we have to break it into its component. Okay, so if this angle is theta, geometry, by using the geometry you can show that this angle is also theta. Okay, then how to break this? As you already know that we have to draw a line from the tip of this vector to this line. Okay, so this is one, and then we have to connect this with this one. Okay, so that's how we break the gravitational force here. So now this is opposite of theta. So when something is opposite of theta, that is the sine function, right? So it will be mg sine theta, and this is adjacent. Adjacent means cosine, so it will be mg cosine theta. Okay, so once we break this, and we know that the acceleration, if there is acceleration, it will be in this direction, then we can write the two equations, one for x-axis, one for y-axis. Okay, so then we can solve it, right? So only thing here is only thing that is different from the regular problem is the axes are now something like this. One is perpendicular to the surface, another is parallel to the surface. Okay, and another thing you have to know is this, and if this is the angle theta, then this angle will also be theta. So here you see, if this is theta, this will be theta. Okay, now so this is mg. Okay, so this is mg. We have to break this. So how to break? So you have to draw a line, okay, that connects the axis, okay, and then this. Okay, now because this is opposite to theta, it will be mg sine theta. Okay, and this is adjacent, so it will be mg cosine theta. Okay, so here you see that we draw, I mean, we did not draw here, instead we draw it here. Okay, so mg sine theta, I mean, this and this are parallel, so this one and this one basically represent the same thing. So once you understand this, solving an inclined plane problem is not that bad. Okay, so we'll be doing some example problem in the problem solving lecture. Okay, but I'm going to stop today's lecture here.